Okay. So, hello everyone. My name is Ihsan Cember. I'm a master's degree student at Istanbul Technical University, the Department of Aeronautical and Astronautical Engineering. And also I'm working as a computational aerodynamics engineer at Turkish Aerospace. So today I will make a presentation of jet noise prediction for nozzle geometry with using OpenFOAM. So in the first part of the study, I will talk about the short introduction of our study case, and in the second part, I will talk about the computational methodology, geometry and boundary conditions, numerical schemes, and the convergence criteria. In the third part is about the mesh studies, and finally, I will talk about the results which is getting in the study for aerodynamically and aeroacoustic data. So there are two main points in the study, and the first of which is about solving the complex flow field. And in order to solve the complex flow field, open source high-speed aerodynamic solver was used, which is density-based and the coupled solver. For aeroacoustic analysis, a lib acoustic module was used with the Fox-Williams-Hawking acoustic analogy, and this code is available in GitHub. So here is the baseline axisymmetric convergent nozzle geometry. This is the technical drawing, and we have a cylindrical computational domain with the given dimensions. So as a boundary condition, characteristic partly boundary condition was used for the external boundaries, and the total pressure is selected for the modeling of the jet flow with the given values in the table. So as a first step, we solved the flow field steady state with the K-omega SSD turbulence model. In this part, we run the simulation 2000 iteration, and we use the automatically pseudo CFL. It's changing with the 0.1 to 50. And the flux scheme is AUSM+up. For transient simulation, numerical settings changed with this table, and the turbulence model selected as an whale turbulence model, and it's used with the backwards time discretization scheme with the given time step size, which is taken from the reference study. And we create two different sections for checking the convergency inside of the nozzle. And you can see how mass flow rate changes with the iteration. And the first part is, you can see the steady part, and after that, we run unsteady simulation. And this one is showing the unsteady part changing of the mass flow rate. So here you can see the center line, lip line, and the other sections for post-processing. And first, we run the steady state run simulation, and we compare our results for lip line and the center line velocity profile for different meshes. And we saw that there is no significant change in the velocity profile for different meshes. And also, we investigate the integral landscape for the LES analysis. It is an initial guess. It's a good initial guess for mesh size, choosing the mesh size. And we saw that in the literature, F parameter is defined with the length scale, integral length scale, and you can see how F parameter is changing with the mesh size. So F mesh 4 is better than the others, so we continue with this size for the other simulation. And also we create two different type of grids. First one is the unstructured trimmer meshes, and the other one is the structured hexagonal mesh. And also we investigate the energy spectrum at the given probe locations, and the black line is our results, and the blue line is the -5/3 slope, and it's we observe that the slopes are parallel, so which is good for us. And here we compare the structured and the unstructured grid flow field comparison and different sections. So and here we can observe that the unstructured grid has much better resolution, much better good resolving for the flow field. And also we compared our results with the reference study, which is performed by the NASA, and they have 200 million cells with the high order scheme. So here we have 40 million cells with the second order scheme. So this is the very high difference. So here we have the unsteady results are presented, and the velocity profiles with the trimmer unstructured grid looks better than the structured one, but it's under-predicted according to experimental data. And also we compared the different stations for the velocity profiles, and again, the unstructured grid better than the structured one, but our results are diffuse faster. So we should try with the higher grid size. So in aeroacoustics, we have 12 visual microphone and visual microphone with the 100 nozzle diameter radius. And also we generate two different permeable surfaces for acoustic data collection. So we compare it also. And here is the far field noise spectrum. And the left one is showing that the comparison of the structured and unstructured data with the reference and the test data. And there is no significant difference between those grids, but it's also under-predicted according to test data. And the right one is the right side of the graph showing that how changing this noise spectrum with the larger and the smaller permeable surfaces. And as you can see, the smaller one is actually larger one is much better than the other one. And this is the overall acoustic sound pressure levels distribution and different visual microphone and unstructured and structured grids. There is no we observe that there is no difference for overall SPN. On the right side, unstructured data is calculating the overall SPN much higher than the larger permeable surfaces. So in this study, open source HISA solver and the live acoustic module used for the numerical calculations. and unstructured trimmer grid and the structured excited grid were compared for acoustic analyzers. Structured grid behaves slightly diffusive than the unstructured one. Similar behavior was observed in this noise spectrum, but the values were calculated lower than the experimental data. So as a further feature works, analysis can be repeated with the finer grid, and less diffusive numerical schemes can be implemented in this code, especially for the aeroacoustic calculations. And also different alias models, such as wall modeled alias, can be examined. Okay, so thank you for listening.
Thank you. Thinking about the structure, how many cells did it have around?
How many cells?
Yeah.
42 million cells.
I mean, like the number of cells around the nozzle.
Oh,
yeah, that's sort of,
so, actually, I don't remember now.
Is that your structured mesh results were very, they took a long time to get 3-dimensional flow, and maybe the resolution around the nozzle was too coarse.
Yeah, actually, of course. Now, actually, I don't remember the size, but of course,
it's important.
Yeah.
I don't know. You can highlight this line with the unstructured structure with certain things in them.
This one?
Yes. So, in terms of to do like any scaling open situation at OBS, output ratios, you need to get low output ratio. So, I'm a huge fan of structured grids. The whole schooling. And the case is that maybe the reason you get better resolution of the stable holding simulation on unstructured is not because it's structured, because it's low output ratio. When you get many high concentration cells in the region of interest with your structured grids, because that's how structured grids are usually made. So did you do like a comparison of what is the active ratio of your structure? So the unstructured model is 1. And in the unstructured grid, you don't have high concentration cells. Basically, you want to resolve part of the spectrum. And if you had high concentration cells in the region, then that's what needs for high concentration on the structure, especially that that there is an delta when you get concentration even higher than 1. So you can use like the cube root of the volume, you can use the highest length in the element, and it never works perfectly with the higher cells. Maybe it's not that the structural approach is bad, it's just that they really need to focus on having the aspect ratio over, for example, the whole region.
Actually, you're right. In here, we focus on the core region, and we try to give a same sign at the core region. But actually, you're right. Aspect ratio at the structured grid is higher than the unstructured one.
I believe it's something similar. In fact, the only answer that you might always about layer and then open up the steel layer. But it's impossible to do if you have it's topologically impossible to do it with a much star and then with the security. So yeah, I know it's the that's there is like unavoidable. Thank you. Okay.
No, Dragon 19, penultimate drive, is going with Dragon 19, it's going Dragon 19, second penultimate drive, that's what it is. go slide number 19, 19.
It's your line number 19.
Penultimate, no, go, 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 where did go? Go. Okay, what is the difference between the left and right?
The left one is showing that the unstructured and the structured grid, and the right one is the different acoustic program.
Yes, it's okay, sorry, okay, so now I didn't read this. Okay, it's my fault.
Yeah, I also wonder, you're using density based.
That's yes, yes, that's
What that means that?
what.
Yeah, why you choose use density
Why,
if it's not the pressure based? That's going to give you totally different results.
In OpenFOAM, there is no density-based coupled solver, and we just try to implicit density-based solver. We just try it and compare the results. So, and also in OpenFOAM, pressure-based solvers are segregated, so delta T increases, and the computational time is dramatically increased according to coupled solver. So,
Right?
yeah.
So it's fine, the density one gives you better.
Yeah. Yeah.
Okay, that's very to know. Thank you.
Thank you.
So, hi everybody. Today I'm going to show you, I'm Alessio, from University of Rome, Ihsan. And today I'm going to show you raw energy form density-based OpenFOAM solver for turbulent compressible flow. And this is a solver that me and my colleagues, Daniele Fontana, we are using right now in our PhD course to, deal with complex geometry for industrial purpose. And the solver, here we're going to have an outline, we're going to have a brief introduction of raw energy form. We're going to see the numerical method inside the solver. I'm going to show you some the test case to show the potential of the solver. And then I'm going to explain you the future works that also we want to do with this particular solver. So OpenFOAM, raw energy form was developed by Professor Davide Modesti and Professor Sergio Pirozzoli in 2017. They wanted to use something that wasn't in OpenFOAM, since we understood that compressible solver in OpenFOAM, especially density-based solver in OpenFOAM, they are not particular for LES or more complex geometry with shock wave in the problem. So they understand that an hybrid numerical schemes based on the mathematics developed by Sergio Pirozzoli and adding the sympathy price with this central part of Sergio Pirozzoli can achieve an energy preserving situation, and also comparing to the already present raw central form solver in OpenFOAM, the result was actually better. And here I'm going to show you the convective parts, convective flux inside the code. Here we can see that the numerical parts, especially the convective flux inside the Euler equation, are divided in convective part and pressure part. And then the convective, each of these terms are divided into the central and diffusive part. So, Professor Pirozzoli proposed a 3 average point flux, then you can see here in this slide. And thanks to this particular flux, if we analyze smooth flow without any shocks inside, we can see that we are able to preserve energy in time. And also the pressure flux is evaluated with an easy central interpolation. But since we have to deal also with complex geometry, we have to use also abstracted mesh. So to stabilize our numerical schemes, we have to add some numerical diffusion. So the idea was to use the flux scheme AUSM+up developed by Liu. And here you can see here that we used the diffusive parts proposed in the AUSM scheme, but they are weighted with a Piccolo sensor, and also they are activated by particular flags. Here you can see EC flags and EP flags. Here you can see the Piccolo sensor that we use inside our solver. And thanks to this particular construction of the schemes, we can reorganize our solver in three particular modes. So mode A, where we don't have any of the flags activated, so the Piccolo is switched off. And here we're going to use only the central part proposed by Professor Pirozzi. And we will see later that that part shows us the energy preserving situation. Then we have mode B, where we use this particular mode for unresolved smooth flow. So, for example, we will see the particular cylinder or stuff like that, kind of the turbulent layer. And we will see that here we activated the EP flag, and we only have diffusion of the pressure flux. And the last mode is mode C, that we use this particular flag when we have short geometries, and for example, I'm for a transonic simulation. So if we go on, and we will see that our idea was to compare raw energy form with raw central form. And here you can see that also we have a summary of what I already told you right now. And here we're gonna see some few test cases. And we're gonna start with the case of tropical turbulence. And this is just a case where we're gonna, quantify the preservation of the energy, and also how much is the dissipation when we activate the different flags. And here you can see the graph where we can have the kinetic energy inside. And as you can see, the right triangle, black right triangle, represent raw energy form in mode A, where, as I said to you, we're gonna let that activated, and we only use the central part proposed by Professor Pirozzi. And here you can see that the energy is still represented during the simulation. And while we activate the mode B situation or mode C, we can see that the dissipation is higher than the mode A. We can see that the energy is not conserved. But in mode B, we can see that the dissipation is less than DNS form. And in case of mode C, where C is typically near to raw central form, we can see also that the dissipation is also low than raw central form. And this is a particular great result because it's a great benchmark to understand how solver, how to deal with the dissipation. And also it's a particular benchmark in case in the future we want to develop other particular dissipated flux. So going on, we can see another important benchmark that we did, and it was the Taylor green vortex. And here you can see that the results that I'm going to show you are just for the structured mesh, but we also performed a simulation on a structured mesh. And for obvious reasons, I'm going to show you only the structural results. But as you can see here, the idea was to enhance the capability of time reversibility of the energy of error equation. And here you can see that the implicit Taylor-Green flow is capable with raw energy form to preserve energy in time and also recover the initial condition. And here I'm going to show you the graph where we can compare raw energy form in mode B, mode A, DNS form, and raw central form. As you can see from these plots, the capability of raw energy form in mode A are perfect. There is a totally preserving of energy, and also we recovered all the initial conditions. For raw central form, it's difficult to see, but here on the graph, you can see that the red dot, they represent raw central form that is unfortunately not capable to preserve energy in time. And I'm going to show you a video, and here I'm going to show you the key criteria and to see how the initial condition and the entropy on the right side, how are they recovered during time. So here you can see that we arrived at maximum. We're going to time reverse the problem. Easily, we are going to simply multiply for -1 by -1 the velocity field. And then we can see that the solver is capable to recover the initial condition of the problem. Going on, we also did another important test case that is also in the tutorial test case of OpenFOAM, and especially for raw central form. And this is the forward step. Here, the idea was to only look if the solver was capable to deal with shocks, and also if it was capable, the curve sensor, to sensor in the read and find where are the shocks. So here I can show you. And here on the triple point, you can see that raw energy form is capable to enhance the slit line, and also that's also the good piece of raw energy form, and that's what we want. That the solver is capable to enhance some particular details that maybe other kind of solver are not capable to find. And going on in the test case we have the Onera M6 irrigation simulation. Here the idea was also to test the Piccolo sensor with a bit of the solver to find shocks, but also to prove if the code was capable to deal with 3D complex geometry. And what we find here that the results were also incredible. And we can see here that even if the mesh was really close, around 300,000 cells, here you can see with the comparison with experimental data, they are good. There is a good fit. And also in the red line, red dot, you can see that raw central form is not totally capable to give enough details of this particular test case. And also here is a better see. You can see that the lambda shock is easily notable here on the wing by raw energy form, while on raw central form you can see that the detail is not totally clear. So this is also another good point for raw energy form. So going on, we also did the DES, and because the idea is also to use this solver not for ULMs, but it's also possible to use it. But the idea is to use this solver for AES or DES to, as I said before, to have all the details necessary to have a great design of industrial shape, like iPhone or Minecraft. So here we can see detail, and you can see a video, the Q criterion of the cylinder, and we can see that here the information are also quite good. So in this case, we understand that the solver is also capable to deal with a wide range of Mach numbers, since we can go from low Mach number, as I said before, with the Taylor Green vortex, or here with the 0.1 Mach number, to supersonic situation where we can have a sharp penetrating limit. And then here is the last test case that I will show you. Here is a simple 2D geometry of an airfoil, especially area 2822. And here you can see that the comparison with raw central form are good, and also you can see that there are quite better results, Compressible results better than raw central form. But here you can see that raw energy form is capable to do everything that raw central form can do, and also to do it better, and maybe it's able to do something better. And in conclusion, here, so I show you that the code is energy preserving, and the capability to deal with a wide range of Mach number, so from subsonic to supersonic with no big problem, and also capability to deal with industrial complex geometry and with both structured and unstructured mesh. Here I have to say that also the solver is quite lower than a little bit slower than the raw central form. The idea is to speed up it. We already did it by using third order rule schemes instead of fourth order and for time integration. But we also try to understand if the capability on HPC optimization is also possible. And we are already dealing with this problem. We already understand which are the limitations in this case. And also in the future, we probably can see if there are also possible other kind of CVD plus schemes that can be better, maybe even AUSM+apps. And that's it. Thank you for your attention and for questions.
No problem.
Yeah, the maximum value was 3 with forward step, but the situation was implicit, so probably we'll see the solid scale works with the higher mass number, also with the balance.
Okay, because the raw central form until number able to balance. After that, they doesn't work because of the.
Well, actually, I think it's a difficult situation even for raw energy form, because you know at that Mach number there are also other kind of stuff to consider. But it's a good point. We will probably try. It's, if the test case to try is easily to have, we're gonna try and let you know.
How do I have very good number? So as I know, that's the base soldier. They have emergency issues are very low. But actually, they in the sense of how these stage are like very
No, actually, we arrived to 0.01 for the Taylor vortex, and we didn't go farther. So, but we can try this. It's also a good point. You know, the range is already wide, so we are okay with it.
Okay. It's, I mean, it's quite striking the amount of participation that there is in all these solvers. And I didn't quite understand what you explained. Do you think it'd be theoretically possible for what makes the dissipation per load from that solver into pressure-based solvers or other system solvers? Would be something fundamental context-based?
Well, actually, the idea is not to move to pressure-based, since the main idea is to deal with transonic flow.
But in theory, whether you think, because I'm used to the pressure-based solvers.
It could be. Well, actually, I don't know, because the way that the equation are structured is really easy, and you know, we have a central part and a diffusive part, and that's it. With pressure-based solvers, since we have to do something iterative, I don't know, actually. It's
the theory has been developed and implemented on ion time difference.
yeah, also.
The
But it's still explicit solver, so it's nothing that is near to pressure-based. So, but I don't know. It's a good point. Honestly, I'm not quite prepared about the implementation of this kind of dissipation flux in pressure-based solvers. Theoretically, yes, it could be possible. You know,
we struggle to do acoustics because of that.
that's also the idea of this solver, to have acoustics. And also, since we are dealing also with Stefano and that today, we had understand that the solver, the idea to use the solver is to start from an already solution, from a solution right from an implicit solver, like EX presented by Stefano. And then from that solution, we're gonna go further and see more details. Probably the other solver can give us, and that's the reason where we can go further and see also information about acoustics. So that's the idea of raw energy form.
I guess you're looking at relatively low cooling numbers.
Yeah, it's not easy. It's not easy. We theoretically, it's not easy. Sorry? Yeah, actually, yes. I already tested it with Spark, K omega and K epsilon recently, so I think there should be no problem right now. But
Is it like in growth expanding solver?
yeah, no, it's transistor. Yeah.
All the things maybe not just.
Yeah, you know, in time, yeah, you don't see statistically steady state situation. Yeah, that's the idea. And also the idea was to show you the code in order that people are going to use it and find any problems to fix it. So that's to improve those.
I think the next year.